A wide-body airliner with hundreds of passengers on board is routinely sailing through evening sky over Japan when a major emergency forces the crew to divert immediately. As the crew begins an emergency descent, they suddenly discover another major problem. Despite the captain's attempts to move the flight controls, the aircraft continues to fly straight. Only several minutes after routine takeoff, the flight crew finds themselves inside a dangerous projectile, traveling nearly at the speed of sound. How did a minor incident from the past turn a passenger airliner into £500,000 of uncontrolled metal, putting the lives of everyone on board in jeopardy? What non-conventional methods can the pilots try in an attempt to save the battered airliner? This is the story of Japan Airlines Flight 123. On the evening of August 12, 1985, a three-man flight crew boarded a Japan Airlines Boeing 747 parked at the gate in Tokyo, Haneda. As the pilots began preparing the aircraft for the departure to Osaka as Flight 123, the flight attendants welcomed travelers in the cabin. Good evening and welcome aboard Japan Airlines Flight 123, developed by Boeing specifically for Japan's domestic travel market. The 747-100 SR, which stands for short range, was modified to carry less fuel and more passengers. Flight 123 was scheduled to accommodate 509 passengers with 2 pilots, 1 flight engineer, and 12 flight attendants on duty, bringing the total number of occupants to 524. In charge of Flight 123 was Captain Masami Takahama. At 49 years of age, he had accumulated 12,424 hours of flying time, with 4,842 hours in the 747. He had been with Japan Airlines for 19 years and held type ratings for 3 other airliners besides the Boeing 747. On Flight 123, Captain Takahama was seated in the right seat, normally designated for the first officer. The captain's role was to conduct training for First Officer Yutaka Sasaki. The 39-year-old pilot had accumulated a total of 3,963 hours of flight time and over 2,600 hours in the 747. Having been with Japan Airlines for over 5 years, First Officer Sasaki was well underway toward his captain upgrade. As part of the upgrade training program, he was seated in the left seat on Flight 123. Accompanying the 2 pilots was 46-year-old flight engineer Hiroshi Fukuda with nearly 10,000 hours of total flight time and close to 4,000 in the Boeing 747. As a flight engineer, he was in charge of monitoring and controlling most of the aircraft systems. At 6:00 p.m. local time, Flight 123 was pushed back from the gate, started its engines, and began taxiing toward the runway. Ending the long day of several short flights, the 747 was headed on another domestic hop from Tokyo to Osaka. The flight linked 2 of Japan's busiest cities. Hence, it was not uncommon for Japan Airlines to have such a high passenger load on this 1-hour leg. Once again, signifying the need for a wide-body aircraft designed specifically for this densely populated Asian country. Within a few minutes after the gate doors closed, Flight 123 was airborne and on its way to Osaka. Chasing the sunset, the aircraft started a gentle climb toward the cruise altitude of 24,000 ft, and the flight attendants provided the passengers with in-flight snacks and beverages. The weather was forecast to be good. The crew was experienced, and as the 4 Pratt & Whitney engines quietly purred over the setting sun, everything seemed perfectly normal. But the fate of Flight 123 changed in just one short moment. A few minutes before the 747 was supposed to level off, a loud blast and a powerful shock wave traveled through the entire aircraft. A second later, thick fog filled the cabin, only further fueling the terror and the confusion of everyone on board. Shocking and unexpected, the fog was the result of the air inside the cabin rapidly cooling and condensing due to a sudden drop in pressure. The fascinating physics phenomenon served as a dire warning that the air inside the aircraft was no longer considered breathable. In other words, the cabin was not pressurized anymore and a descent was necessary. Following the explosion, the crew of Japan Airlines Flight 123 immediately declared an emergency with air traffic control and began planning a diversion. Flying directly over the Izu Peninsula just southwest of Tokyo, the pilots requested a descent to 22,000 ft and a return back to Tokyo via Oshima, a small island just off the coast of Japan with a radio navigation beacon. Moments later, ATC instructed Flight 123 to begin a right turn heading eastbound. As he watched the aircraft on the radar, the controller noticed that something was amiss. Instead of making a turn toward Tokyo, the 747 turned slightly to the right and continued to fly toward Osaka. Uncertain of the reason, but suspecting that something was not correct, the ATC radioed the crew to verify that there was an emergency on board, requesting further details. A response did not follow. After a long and deafening minute of silence, the controller instructed Flight 123 to once again turn right and take an easterly heading. The pilot's immediate response alerted everyone on the ground as it became obvious that the situation had significantly escalated. JAL 123 now uncontrollable. Following the loud explosive decompression that caused the sudden drop in cabin pressure and required an immediate descent requested by the captain, the airliner entered long oscillations up and down along its longitudinal axis. Combined with a yawing motion that swung the tail side to side, commonly referred to as the Dutch Rom, the 747 was no longer flying straight and level, instead bouncing around in the air. None of the pilot's attempts to stabilize the airliner worked. The control surfaces were not responding to any yoke inputs as if they were detached. Although nobody on board the aircraft fully understood what had just happened only seconds after the initial turmoil, an unpleasant discovery by the flight engineer confirmed the worst possible outcome. Scanning numerous cockpit instruments for abnormalities, he noticed a loss in the aircraft's hydraulic pressure. The hydraulic fluid, a vital component in a large airliner, is required for operation of most flight controls as well as flaps and the landing gear. The fluid drives the actuators that move the control surfaces, and its loss would explain the inability to control the aircraft. Without the adequate pressure in the hydraulic system, the 747 became a large and uncontrollable hunk of metal. There was only one way the crew could still manage the direction of flight. It wouldn't be precise, but it could work as long as the engines were running. By adding more power to the engines on one side only, the pilots could create a difference in thrust that would be enough to push the nose of the aircraft in the opposite direction. It would also accelerate the wing on that side, resulting in a higher lift force. The resultant yaw and bank could be used to change the aircraft's heading. To make it climb, the pilots would add power to all four engines at the same time, increasing the aircraft's air speed and lift force. In a similar fashion, reducing engine power could help the crew descend toward the ground. Using only engine power for aircraft control was going to be hard and inaccurate. Furthermore, using differential thrust would not stop the Dutch roll and could even worsen it. However, it was the only option that gave the crew a chance at a safe landing. As the pilots continued to work out the controls, the aircraft flew over the Suruga Bay toward Shizuoka, passing just south of the city. A minute later, ATC radars detected a change in its direction as the 747 turned right, flying north. Watching the change in heading on the ground, the Tokyo approach controller offered the crew to turn west toward the Nagoya airport, some 70 miles away. In response, the pilots of Flight 123 requested a return to Tokyo. Although slightly further and not in the direction of flight, this choice made sense. Haneda Airport had a longer runway and the emergency services that were likely to be needed. After another minute of flying northbound, the airliner turned further east and started moving in the general direction of its departure airport. At the same time, the pilots decided to extend the landing gear using a backup method designed specifically for an instance when hydraulic power is lost. Instead of the hydraulic actuators, electric motors released the locks that keep the gear restricted, letting the heavy wheel assemblies drop under their own weight until they got into the extended position. The gear sticking out from the bottom of the aircraft generated significant aerodynamic drag, and the airliner began a gradual descent from 22,000 ft. During the next 10 minutes, Flight 123 continued moving in the general direction of Tokyo, including a full 360 degrees turn over the mountainous terrain northeast of Mount Fuji, while the pilots did their best, fighting the uncontrollable giant. 45 minutes after the 747 lifted off from Haneda Airport, the airliner was back in the vicinity of the airport, flying at 9,000 ft, only a few minutes from reaching the runway. But in the next minute, the airplane, still barely controlled by the pilots, made a left turn and began flying farther away from Tokyo. Descending through an altitude of 5,300 ft, the crew noticed mountains straight ahead and applied full engine thrust, sending the airplane back to 13,000 ft. On the ground, several residents of a small village in the heart of Japan noticed an unusually terrifying sight: a large airliner flying right at them at a surprisingly low altitude. With no airport in the direct vicinity and mountain ranges nearby, it was a worrying sign. And even more worrying was seeing the aircraft bank to the right and begin a deep dive toward the terrain. A few short seconds later, the 747 disappeared behind a mountain, and the peace of a quiet evening in rural Japan was restored. Only a large plume of smoke in the distance marked the end of Japan Airlines Flight 123. What exactly happened in the final moments of the flight? The sharp nose dive and the steep turn observed by the witnesses on the ground were caused by the extension of the wing flaps. Possibly in an attempt to regain some control of the aircraft, the captain decided to lower the flaps using the alternate flap extension system that relied on electric motors. However, instead of stabilizing the aircraft, this action created slight changes in lift generated by the wings, and the 747 started a bank to the right. The situation worsened, prompting the crew to retract the flaps back. Despite the pilot's best efforts, the airliner banked beyond recovery, and flight crew inputs made no difference to its position. The Boeing 747 struck several mountain ridges as it continued its high-speed shallow descent before crashing into a mountain a little over 0.5 miles past its initial point of contact. Of the total 524 people on board Flight 123, only 4 lived to tell the horrors experienced on the fateful night of August 12, 1985. How did a marvel of aeronautical engineering, commonly dubbed as the plane that changed air travel, end up in what is still considered the deadliest single aircraft aviation accident and the deadliest accident in Japan? In a rather surprising turn, the long chain of events that brought down Japan Airlines Flight 123 began on June 2, 1978, on another flight to Osaka. During a rather hard landing, the aircraft struck its tail on the runway surface, causing significant damage to the tail section of the fuselage, including the pressure bulkhead. The vital role of this bulkhead in the aircraft structure is to hold the pressure inside the cabin as the aircraft climbs to higher altitudes. Therefore, its integrity is crucial. A team of Boeing engineers was dispatched to repair the aircraft, but identified that the placement of several rivet holes on the new bulkhead did not conform to the specifications, and a reworked design was required. The reinforcement involved installing an additional plate between the 2 metal pieces of the pressure bulkhead connected by 3 rows of rivets. During the actual repair work, however, the technicians deviated from the original plan and added 2 plates installed parallel with each other. The seemingly minor difference weakened the metal structure. Over time, the frequent cycles of pressurizing and depressurizing the cabin during numerous daily flights created extensive loads on the pressure bulkhead, and minor fatigue cracks began to form around the improper repair. Virtually invisible to human eyes and therefore undetected, the cracks continued developing for 7 years through thousands of flights. And on August 12, 1985, at around 1824 local time, the cracks reached the point at which the weakened metal could no longer withstand the forces. The strong cabin pressure acting on the metal with the force of nearly 9 lb per square burst through the growing fatigue cracks, tearing metal apart and filling the empty space of the unpressurized empennage behind the passenger cabin. Within seconds, the destructive air reached the tail fin of the 747, shearing parts of the rudder off the airplane and damaging the elevators. The force was so strong it almost instantly ruptured all of the aircraft's hydraulic lines that were routed through the rear portion of the fuselage. Without a portion of its tail, the 747 was no longer aerodynamically stable, and without the hydraulic fluid, the pilots were not able to properly control the aircraft. Both factors combined lead to the oscillations and the Dutch roll which the crew of Flight 123 continued to fight for the remainder of the tragic flight. After a lengthy investigation, Japan's Accident Investigation Board determined that the improper repair was the root cause of the accident. Although the long-term maintenance schedule involved multiple heavy checks throughout the years as the cracks were developing, they were never identified. The maintenance inspection program was mainly focused on monitoring for corrosion because the area around the pressure bulkhead was considered strong enough and fatigue cracks were not expected to develop. Furthermore, the fail-safe design of the bulkhead accounted for metal fatigue, but only if it remains within one area. It was never assumed by the engineers that several fatigue cracks too small to be detected would compromise this aircraft component. In a more somber turn of events, coroner's estimates revealed that dozens of people survived the initial impact. But the location of the crash site, rooted deeply in the mountainous terrain, hampered the rescue process, and many people succumbed to their injuries before help arrived. Furthermore, the death toll from Flight 123 did not end at 520 people who perished on the day of the crash. Within a few years of the tragic accident, 2 maintenance workers involved in the repair, including one of the engineers who signed it off, ended their lives. Perhaps the most disheartening aspect of Flight 123's story is that 17 years after 520 people perished in the mountains of central Japan, history repeated itself in the most cruel way possible. In 2002, another Boeing 747 operated by China Airlines disintegrated mid-flight over the Taiwan Strait due to a developing fatigue crack in the fuselage, killing all 225 passengers and crew on board. But more disturbing was the cause of the fatigue crack, a deviation from the approved repair procedure after a tail strike that had occurred 22 years earlier in 1980. The loss of 745 lives between the two accidents will forever serve as an eternal reminder of how dangerous latent errors can be. Unlike active errors, which typically lead to immediate consequences and are caught early on, a latent error may remain hidden for long periods of time before its outcomes, sometimes catastrophic, reveal themselves. These errors highlight the high stakes in which every aviation worker operates. Every repair, inspection, and component carries the weight of every life that boards the aircraft.